All right, well, welcome everyone. Good afternoon, and welcome to today's joint EOL RAL seminar. I'm Sarah Woods, and on behalf of EOL and RAL, I'm pleased to introduce Dr. Sarah Tessendorf. Dr. Tessendorf received her BS in meteorology from the University of Nebraska and her PhD in atmospheric science from Colorado State University. Currently, as many of you know, she is a project scientist in the Research Applications Laboratory. In her current position, Dr. Tessendorf oversees numerous cloud microphysics research projects, including many on winter orographic cloud seeding, and is the interim science deputy of the Hydrometeorological Applications Program in RAL. Dr. Tessendorf was a principal investigator of the seeded and natural orographic wintertime clouds, the Idaho experiment, also known as SNOWY. She has published over 50 peer-reviewed journal publications and won several UCAR Outstanding Accomplishment Awards, including for mentoring, diversity, and an Outstanding Publication Award for her BAMS paper on SNOWY. She co-chaired the American Meteorological Society Committee on Planned and Inadvertent Weather Modification for the past 6 years, and currently co-chairs the World Meteorological Organization Expert Team on Weather Modification. Please join me in welcoming Dr. Tessendorf for her seminar titled Aviation Hazard or Precipitation Enhancement Opportunity, the Implications of Supercooled Liquid Water in Wintertime Clouds.
All right, good afternoon. Thank you so much for that wonderful introduction. I'm really excited to be here. Great to see this turnout of folks that are interested to hear about some of the really cool work that we've been doing over the last few years, especially with the SNOWY project. So I wanted to just start off with a little bit of a quiz, although in this audience, and for anybody that just read the title on the screen, you might already have an idea what the common link between these photographs is. But I will jump to the fact that they have supercooled liquid water in common. The leftmost photograph is showing an aircraft that has undergone heavy icing due to supercooled liquid water that it flew through. And in the center is an aircraft being outfitted with cloud seeding flares, silver iodide flares, targeting supercooled liquid water to transform it into snow. On the right, that's another form of cloud seeding, but this time from the ground. That's a photo of a ground-based generator that burns a silver iodide solution, again, targeting supercooled liquid water in clouds in order to form snow. So on this topic of supercooled liquid water, it exists in our atmosphere when liquid drops do not freeze once they get colder than the freezing point. And the reason for this is because ice does not form until spontaneously without any type of ice nucleating particle until temperatures as cold as -40 Celsius. So in this region between 0 and -40, we tend to have what we call mixed phase clouds, where there may be some ice, but there's typically some supercooled liquid water present. And when it comes to aircraft icing, the icing threat, where you have the most supercooled liquid water content, is in that 0 to -15 degrees Celsius range. And on the right, I'm showing an image over here from DeMott et al. Showing the ice nuclei concentration versus temperature, and all the points on here are from different measurement campaigns. And you can see one of the reasons for this is that especially warmer than about -10, you don't tend to have ice forming naturally from ice nucleating particles. So this presents an aviation hazard called aircraft icing for clouds with supercooled liquid water, where that liquid water then freezes on to the subfreezing temperature of the airframe as it flies through the clouds. But it also indicates that ice phase precipitation formation processes are not efficient. And there comes in this opportunity for precipitation enhancement. So this is a schematic walking through the conceptual model of cloud seeding to enhance winter orographic precipitation. The purpose of this is usually to enhance snowpack, but also sometimes subsequently streamflow is the other real aim in trying to enhance precipitation in the mountain regions. This is all based upon this understanding that clouds can contain supercooled liquid water. So that first step in this whole conceptual model is that a cloud is forming over the mountains due to the airflow of the mountains, and that cloud contains supercooled liquid water. The next step then is that you can release silver iodide, which is the primary nucleating agent used in most cloud seeding. It is the subject of most of our research in our group. That can be released, as I showed in the prior photographs, from a ground-based generator or released from an aircraft. An important step in this process then is that those particles disperse and get into the cloud where there's supercooled liquid water at temperatures where that silver iodide will nucleate ice. Laboratory measurements have shown that silver iodide can nucleate ice as warm as -4 or -5 degrees Celsius. So again, you can see from that prior chart that showed that most naturally occurring ice nucleating particles don't become active until colder than -10 degrees Celsius. There's already a window of opportunity where silver iodide is going to nucleate ice potentially warmer than what might be occurring in nature. Once that silver iodide nucleates ice, then the Bergeron-Van process kicks in, and that ice will rapidly grow at the expense of the supercooled liquid water in the cloud, thereby producing the snow that falls to the ground. So the overall conceptual model is trying to convert that extra liquid water into additional snow. So the origin of this concept has been around a really long time. It was discovered in the 1940s. And there was this iconic photograph shown here of a racetrack pattern flown through a stratocumulus cloud with supercooled drops. This was published in Life magazine in 1946. It was very clear evidence that we can have an intentional impact on the clouds. In this case, it was dry ice seeding that was used there. But that was the moment that a lot of scientists got really excited about the promise for us being able to maybe control the clouds, control the weather. In this case, hey, if we can make this cloud glaciate like this, we can use this to enhance precipitation. But in fact, it's taken over 70 years to really prove that entire conceptual model, because what we see in this photograph is just the first couple steps in that whole conceptual model where we're altering the cloud, but then measuring the impact on the ground in a clear way has been very challenging. Part of this is because there's a lot of natural variability in the weather and precipitation in itself. And so it's really hard to identify what would have happened naturally, right? So that's one of the challenges. The other is a lot of these programs tried to use statistics. And if you have a large natural variability in your sample and maybe your signal that you're looking for is small relative to that large natural variability, you need a really large sample to overcome that and create statistical significance. And the large samples were, like most of these programs went on for several years, but either that signal was too small, natural variability was too great, or overall the sample was not sufficient to really get that high level of statistical significance to conclusively say that effect was due to seeding and not to chance. The other thing back in the 40s, 50s, and 60s is that the observations and the computer modeling capabilities of that time are quite different to what we have today. So if we fast forward to present time, and in particular in 2017, we've been able to make a lot of advances. We went into the field in Idaho for the SNOWY project, which, as Sarah, you articulated a lot of big words in that introduction. Seeded in natural orographic wintertime clouds, the Idaho experiment. That's our fun acronym that we created for this project. It was a 10-week-long program funded by the National Science Foundation as well as Idaho Power, and we also have some funding that came in from the Bureau of Reclamation for this research. We brought together a team of investigators from several universities as well. I put some names of folks that participated in the project on this slide. I want to also acknowledge there were a lot of students, and there have been a lot of other people working on our papers that I'm going to be talking about results from. But we had this really great team that went into the field to study cloud seeding. However, the N in SNOWY stands for natural on purpose. One of our first goals for SNOWY was actually to better understand the natural processes by which precipitation forms and evolves. In particular, we proposed some hypotheses that there would be a role of mesoscale and microscale dynamics and of the underlying terrain on the formation and fallout of ice. And so we wanted to better understand that, because we have to understand the natural clouds if we want to better understand what impacts we might be having from cloud seeding. The second big goal was then to determine the physical processes by which cloud seeding with silver iodide is impacting the snow falling across the river basin. And we proposed an approach that not only combined these novel observations and advanced observations, but we also combined that with model simulations. And it was really important that we collected these observations to then evaluate and improve some of the new modeling capabilities that came about in the last decade, such as WRF weather mod. So our field experiment focused on the Payette River Basin, which is north of Boise in Idaho. We had the University of Wyoming research aircraft that had a lot of in situ probes, as well as the vertically pointing W-band cloud radar. We also had another aircraft that had the seeding flares on the wings, as well as an ejectable flare compartment below the aircraft that was operated by Weather Modification International. We had 2 Doppler on wheels radars that we put up on top of the mountains to fill in some of the gaps where NEXRAD in the area does not adequately see. On the map shown here, the black pluses with circles. Let me see if I can get this pointer to work. There we go. Those were our 2 DOW locations, with this one here at the Packer John location being a focal point for our Wyoming King Air flight tracks. It always intersected over that DOW. We also launched extra radiosondes. We deployed additional high-resolution snow gauges. We had some microwave radiometers. And then there were also a suite of ground-based generators around the area. However, our primary focus for the experimental design was on the airborne seeding. And the reason for this is because we hypothesized with this cartoon here, which was substantiated by some of our early model simulations, that if you were to, in this case, that we've got a westerly wind, if you were to have your seeding aircraft fly a straight line track back and forth, this track being perpendicular to the wind, that as it's releasing the silver iodide, it will disperse downwind in a zigzag-like pattern. And then our goal was to fly the Wyoming King Air with its research instrumentation along the wind, so it would fly in and out of these different seeding lines, so to speak, and we would be able to detect the enhancement in ice concentration due to the seeding. So we wanted to focus on airborne because of this potential for creating a very unambiguous pattern in the clouds, similar to that racetrack pattern from the earlier photograph. So we were in the field for 10 weeks, and it was a very successful field project. I'll talk at the end about why I think it was, but I mean, one of the things that took place is we got 24 IOPs. We collected data in 24 cases over that 10-week period. We were hoping for 10 to 15, right? And any of you that do field work, you know how it is. You put a climatology together, you propose you're gonna fly this many hours, and maybe you get half of that sometimes. We got way more. It was a very active winter, so we had some good fortune on our side. In fact, so this chart over here is SNOWTEL precipitation accumulation over the 10-week period of the field project, and you can see that the blue line is the accumulation of precipitation from 2017. The red line is the median, the 30-year median over this period. We ended up experiencing the second wettest year in that 30-year period. No, it was not due to the cloud seeding, but it was very fortunate for us to be out there collecting measurements in a very active winter. Of our 24 IOPs, 19 focused on airborne seeding. We had 3 with ground-based seeding, and we had 3 that didn't have any seeding at all. And so we were able to utilize both aircraft for some detailed measurements. The other thing that was fortunate about having this large number of sampled cases is that we also sampled a wide variety of cases. And so we had several atmospheric river events that impacted the region. We had cases that were shallow orographic clouds. Oops, I hit the wrong one. Go back. Nope. Sorry, I'm getting used to this remote. All right, we had some cases like this with shallow orographic clouds. We had some deep stratiform cases. We had these multi-layer clouds and really complex structures, and we even had a few with some embedded convective features. So we got a lot of different data to look through for a lot of different purposes. So this data really provided us with a lot of new insights into mixed phase orographic cloud microphysics. And specifically, 3 things that I'm going to walk you through in today's seminar that we've been able to utilize the data for are studying generating cells microphysics, supercooled large drop aircraft icing, and the silver iodide microphysical response. So starting with the generating cells, we observed these frequently in snowy. The way we observed them was with the W-band airborne radar data. These were very fine scale features, cellular features that have a trailing echo below them. They are fine enough scale that they're generally less than 1 kilometer in width. Most of them were even less than 3 to 500 meters was the most common size for these. So very fine scale. Even if you had NEXRAD coverage in this region, it might not be able to really resolve these fine scale features. We observed them again in cases like this, very simple cases. Where's my pointer? Very simple cases with the shallow orographic cloud case. We observed them in cases where we had upper level clouds, which initially you would think might change the radiative balance a little bit. And we had cases as well where we observed them with warmer cloud tops and colder cloud tops here as well. So we looked into the in situ data from these few cases where we flew the aircraft. The research aircraft was not intending to fly through these, so we only had a few cases where we got this in situ measurement in the tops of these generating cells. But we did some analysis to look at the in situ microphysics, and then we've also done some analysis of all of our cases to look at the sounding data to see what environmental conditions are they occurring in, so we can get some new information on what their formation mechanisms might be. So from some of the initial segments, these are 4 different flight segments from 3 of the IOPs where we flew through the cloud top. We're now looking at the in situ measured vertical velocity. The blue box and whisker plots are inside the generating cells, and the green are from in between the generating cells, around and outside of the generating cells. So just based on this alone, we saw this common characteristic that the vertical velocities were always greater inside the generating cells than the surrounding area. The other things that we saw, and now these are including even more flight segments, still from the 3 IOPs where we flew through the tops, but we pulled in a variety of flight segments. Blue is still indicating generating cells within them, and the green is outside and in between the generating cells. So each of these pairs of box plots is showing a flight segment. These are also in order of the median ice concentration in them. So you'll notice on the right, this is the 2DS ice concentration greater than 100 micron. You'll see those are going down in order. You'll see almost the opposite trend for the liquid water content, because in the cases where we see the least ice, we tend to see the most supercooled liquid because it hasn't been depleted by the ice. But one of the things that we saw is that the liquid water contents are greater inside the generating cells than around and outside of those generating cells, and the ice concentration is also greater. Even in these cases on the right, where we have very low and negligible ice concentrations, if there's ice, it's inside the generating cells. So these measurements were indicating that these generating cells are really focal points, fine-scale focal points for precipitation formation. So we wanted to know more about why are they forming, what's causing this formation. And there had been some prior studies, especially with modeling that was done, suggesting that it could be cloud top radiative cooling, mechanical turbulence due to wind shear, things like that. So we wanted to look at the sounding data to see if we could gain some insights on what are the environmental conditions when we see these generating cells at cloud top. I'm only showing data of the theta E profiles. We looked at wind and other things too, but the primary thing that we found is these very shallow instability layers at cloud top when we saw generating cells. So the theta E profile in blue here, when it dips negative, and I apologize, these are really small and hard to see because they're really shallow just at cloud top, these subtle, like these small instability layers. So we saw that in our cases with generating cells. And then we didn't have many cases without generating cells. So sample-wise here, we're a little bit biased on the generating cell side, but we have some cases where we didn't see any in these like really deep, really stratiform clouds, like on IOP 23. And in that case, we have very stable positive d theta EDZ profiles. So that was one contrast that we saw, that we tended to see these negative d theta EDZ just above cloud top or at cloud top in the cases with generating cells, where it was stable in the cases without. There were a few cases where we did have some evidence of potential mechanical turbulence as being a cause as well. But in most of these cases, in fact, these couple that I'm showing right here, there was no wind shear at all. So it was really this cloud top instability that was linked to the generating cells. Now, in maybe a future seminar, we'll hear from Lu Lin and others who have done some modeling to better understand these mechanisms of these cases as well. And we are seeing evidence in the modeling that suggests it's due to cloud top radiative cooling. Even in the cases where we have multiple cloud layers, where you might think that the cloud top radiative cooling, say, of this, let me patiently wait for the mouse to come down, of this lower layer might be modulated, we are still having suggestions in the model simulations that that's the cause. So just a recap of this segment, generating cells were observed very frequently in snowy. They were typically sub-kilometer scale features that had enhanced vertical velocity, as well as enhanced drizzle and or ice concentrations. Because these are sub-kilometer scale, you can imagine that our forecast models that are at best 3-kilometer grid spacing are not resolving these features. So that's something else that our group is working on, is to see how we might parameterize the ice production in these in ways that so that our forecast models can better represent that. And that's why it's important for us to understand the environmental conditions that are causing these so that we can set up such a parameterization. And so from this investigation, the environmental conditions indicate that shallow cloud top instability layer is that common attribute of the clouds with the cloud top generating cells. But certainly there's more work that I would like to do in this area, perhaps with some future field campaigns, so stay tuned. So now moving on to the second topic I want to cover. Another thing that was really interesting about the clouds we observed in Snowy was that they had very low cloud drop number concentrations. This is Idaho. It's not along the coast, it's inland. We were not expecting these clouds to have cloud drop concentrations so low of, they're in order of what we typically would see over ocean, marine, maritime locations. In the first 9 IOPs, we didn't see anything greater than even 50 per cc. But generally across all of these IOPs, it was less than 100 per cc cloud drop concentrations, with the exception of that last IOP 24. Even still, it was just a little bit above 100, right? Because of this, we also saw that these clouds had much larger broader droplet spectra because of those low cloud drop concentrations, and they frequently produced supercooled drizzle. So getting back into the topic of aircraft icing, that production of freezing drizzle, it poses a unique hazard to aircraft. So aircraft icing has been somewhat known as a aircraft hazard for a while, but it's only been in more recent years that the FAA has started to recognize supercooled large drop as its own category of icing that required rules, which are referred to as Appendix O, to provide aircraft certification guidance for SLD icing. Not every aircraft that's certified to fly in icing is really suitable for flying in supercooled large drop icing. And the reason for that, from these photos, if you couldn't tell, sometimes supercooled large drop icing produces really remarkable ice buildup on your aircraft. So between changing the shape of your airframe and the weight of your aircraft, that's a problem. That was my husband's flight, by the way. Yeah. This gets close to home, right? But it's also, these drops, because they're larger, they don't freeze on contact as readily. So this is a photo from Snowy down here in the lower right, where this is the wing, and the aircraft has these boots that inflate to pop the ice off. But you can see ice is accumulating just behind those boots rather than it freezing right on them. So it can kind of cause that rollback effect before it actually freezes too. So it's a problem. It has caused accidents. That's what brought everybody's attention to it. And so we want to know, how well do we forecast this? The aircraft icing group has been working to improve and develop products for this. And so one of the things that we did with the Snowy data was see how well the model, in particular the HER model, explicitly forecast this. And to do this, we had to dig into the rules of Appendix O. They define these different categories of supercooled large drop icing based on the maximum diameter of the drops. And so freezing drizzle is defined with a Dmax between 100 and 500 micron, whereas freezing rain is a Dmax greater than 500 micron. And kind of everything else, generally the smaller drop icing, is still governed by Appendix C. So because of that frequency of freezing drizzle in our Snowy data, we utilize this data for some model comparisons and evaluation. So this is an example of a case from Snowy where there was widespread icing. On the left, you can see the supercooled cloud water field forecast by the HER. The red line is the King Air flight track as it flew through these clouds. In the middle panel, we're looking at the model forecast of supercooled rain. So the rain category in the Thomson microphysics scheme is meant to cover drizzle and rain size drops. So you can see there are these pockets of supercooled rain already being explicitly forecast. And some of the work we did was to develop ways to diagnose what the Dmax would be from that microphysics output to see if the Thomson microphysics scheme, which is a bulk microphysics scheme, if it was versatile enough to forecast Dmaxes that were freezing drizzle size versus freezing rain size. And so in this case, It was a freezing drizzle case where all of the blue shading is indicating Dmax less than 500, so it would be freezing drizzle. And so that did, this forecast ended up capturing the event fairly well. Part of the reason for that is the forecast sounding and thermodynamic structure shown on the right shows a fairly shallow cloud layer with cloud tops around -10, prime freezing drizzle type sounding, and that's very similar to what was observed in this case. So then we went and we looked at all of the snowy data to see how well does this microphysics distinguish freezing drizzle from freezing rain. But to do that, the model has to first forecast the SLD, the supercooled large drop icing. That was the biggest challenge. The probability of detection of the HRR model for explicitly simulating supercooled rain, or SLD, was quite low. So I've underlined when the HRR forecasts the SLD, then we can do this detailed comparison of how well the microphysics distinguishes freezing drizzle from freezing rain. And it did fairly well. So this is a heat map on the right showing the observed Dmax on the bottom and the HRR Dmax that we diagnosed on the vertical axis, and you can see that the heat map shows that the majority of points were well within the same category of freezing drizzle. We also looked at this for another aircraft icing study called BEARS, the Buffalo Area Icing Research Study that took place in the Buffalo area near New York. In that study, they had some cases of SLD icing that were freezing rain sizes, so it was a nice data set to look at some freezing rain. The model does a fairly good job of getting freezing rain, that warm nose thermodynamic structure that leads to your classic freezing rain. And in this case, the Dmax algorithm did also show those observed cases of freezing rain that were also forecast. And there were a few freezing drizzle cases as well that compared fairly well. But overall, as I mentioned, because the HRR forecasts really struggled to predict the dynamics or the thermodynamic structure of the clouds that were conducive to SLD icing, that is something that still needs to be improved in the model in general. So a quick recap from this segment is that the model microphysics that are running in the HRR, it's the Thomson-Eidheimer microphysics scheme, were shown to be able to distinguish the freezing drizzle from freezing rain conditions, but we need improvements to the forecast models to better represent the thermodynamic structures that influence cloud depth and cloud top temperature to better predict SLD icing overall. All right, my last segment, which is a really exciting one, because this was a major highlight from Snowy that many of you might have already seen before, because I've talked about this in a few forums. But again, if you recall that cartoon of the zigzag that we were hypothesizing that we might be able to see and be able to detect, the good news is we did. And let me tell you, in the field, when this case was observed, it was, yeah, we were all very excited. So what we're looking at now is an animation of the Dow radar reflectivity in a case that had southwesterly winds. So the seating aircraft is this yellow line. The orange dot is the aircraft flying back and forth at these different times, if you're able to see that. But when the animation restarts, you'll see that there was really no reflectivity echo. This cloud was supercooled, hanging out there, but not producing ice and precipitation readily on its own. And then once we started seeding, you can see that zigzag pattern. It really shows up quite clearly about here. Some very clear and unambiguous evidence of cloud seeding. However, the other thing that made this particular animation very impressive was that, I don't know how many of you heard about the APIP-induced snow at Denver just a few days ago? Yeah. So we saw some APIPs, aircraft-produced ice particles. We saw some APIPs during Snowy as well. So how do we know that this is an APIPS? Well, in this animation, a few of the flight legs were seeded. So the aircraft wing burns continuous silver iodide flares. If we do ejectables under the aircraft, they usually release them about every 30 seconds. There are a couple flight legs in this case where they only used ejectable seeding flares. And you will see here in a moment a dotted line pattern right there come up from those seeding lines. So if it was aircraft-induced ice particles, we wouldn't have seen that separation in the echo. So again, further exciting evidence that we feel very confident that this is due to the cloud seeding. What's more is that coming out of the field very quickly, we were able to detect these and pick out these seeding lines in 3 of the IOPs very clearly. These cases did not have a lot of, or any really, background precipitation, so those patterns were readily detectable. And so we were able to do a lot of in-depth study of those seeding lines, and including we were able to then use the radar data. Here is the W-band aircraft data. Each flight leg over time, we can track those seeding lines to the ground. We can also zoom in and look at the Dow radar data as these seeding lines passed over our snow gauge network. So in this case, we're looking at a zoom in of the Silver Creek site, and in the bottom right, we're now looking at a time series trace. The blue is the measurement in the snow gauge. The gray is the radar reflectivity showing that seeding line, that enhanced reflectivity passing over. So we were able to quantify with snow gauges how much snow was falling out of these seeding lines. And because we measured it in 3 different cases, we were able to use snow gauge data from these 3 different cases to see that we would measure anywhere between 0.05 to 0.28 millimeters of liquid equivalent precipitation increases during these seeding line passages. In addition to that, we also used the radar data using radar reflectivity to snowfall relationships, or ZS relationships, to estimate and then spatially map out the quantity and location of the additional precipitation. For those familiar with ZS relationships, there's a lot of uncertainty in them based on snow characteristics like the density and so forth. The literature has a number of different relationships, so we used them all because we didn't have enough data to create our own here. We used them all, and we actually created a mini ensemble where we varied the A and B coefficients of those ZS relationships so we could kind of capture some of the uncertainty of those relationships. And we overlaid them with the actual snow gauge data, which are shown by these small dotted lines, which showcased that this spread did generally encompass what we observed. Then we took the best match ZS relationship to then map. Using that one ZS, we mapped out what our best estimate of snowfall enhancement from those seeding lines was in each of these 3 cases. This was published in 2020 in the Proceedings in the National Academy of Science. This was a huge breakthrough to be able to not only say we've seen clear evidence of seeding, but we now can map it out spatially and give an estimate of the magnitude over that spatial region from the seeding. And using this ZS relationship, it was around 100 acre-feet to up to almost 300 acre-feet of additional precipitation that was measured in that time. We had a range due to the ZS ensemble. So again, that was using the best match, but we had ranges, but generally it was on the order of hundreds of acre-feet of additional precipitation. So we were able to show and totally prove that entire conceptual model that ice and snow formed in those supercooled clouds treated with silver iodide. That snowfall fell to the ground and was measured on the order of several hundred acre-feet over those 3 IOPs with those unambiguous seeding signatures. Using a combination of modeling and observations, we're also now studying the other IOPs from Snowy, especially those that had background precipitation. But I would like to take a moment and mention, since the initial findings of those 3 cases, we've found at least 3 others where we were able to detect the seeding signatures. We just had to look at the radar data a little bit differently with constant altitude PPIs so that we could get up above where some of the natural background precipitation was occurring. So it's been very exciting that we were able to detect them in other IOPs. And that zigzag pattern has been seen on NEXRAD now in areas where there's cloud seeding happening with aircraft, where they're closer to NEXRAD. So once we kind of showed what you're looking for, people are starting to see it out there more often. So I'm not a modeler, so I'm not going to show modeling results, but I do want to showcase, one of the other major advances that we've been able to do with Snowy is really utilize and verify WRF weather mod, which is a model here. This animation is kind of showing how it works, where you can insert silver iodide in this animation. It's being inserted at an aircraft altitude, and then you've got your cloud water in white, the ice crystals are nucleating in yellow, and the snow is falling out in the green colors. It's WRF, so you're going to get snow falling naturally, but what we do with WRF weather mod is we run a simulation with seeding, we run the same simulation without seeding so we can look at a difference between the 2, and that's how we can spatially map out and quantify estimated impacts of cloud seeding with the model. So it gives us a controlled study. And one of the other things that we do then is we have started running it with an ensemble modeling method because, as you can imagine, the model has its own sources of uncertainty. One single simulation may not perfectly represent a given case. And so we've been developing and demonstrating running with different initializations, running with different physics parameterizations so that we can build up a spread of realizations of what that case might have looked like. And then the other thing that we're starting to do now as well is drive WRF Hydro with the output of WRF Weather Mod. So WRF Hydro is a spatially distributed hydrological model. And because I mentioned at the beginning, some of the programs that do cloud seeding are actually ultimately interested in stream flow. It's important that we try to get from the precipitation enhancement all the way to what the stream flow enhancement might be. So this is an example where we've run an ensemble of WRF Weather Mod simulations shown in the middle. And so it's looking at that ensemble mean seeding effect in inches. Then we drive that through WRF Hydro, and we can map out spatially which basins and how much stream flow change we're seeing as well. So in summary, SNOWY collected an unprecedented data set to study cloud seeding. We had breakthrough observations on the impact of cloud seeding, but we also have a data set that's been great for studying a lot of things about winter orographic clouds, those natural precipitation and cloud processes of generating cells, and it's been able to be utilized for aircraft icing research. However, I do think that computer modeling, which I gave that little teaser of some of the capabilities that we've developed at the end here, that's the future of cloud seeding research and evaluation because we can control the experiment. However, as an observationalist, we still need those observations to constrain and understand how well the model is performing. So I mentioned at the beginning, I would talk a little bit about why SNOWY was so successful. So these are a few of my thoughts on that. First and foremost, the fact that we focused on that airborne seeding mechanism, which produced that unambiguous signature, was critical. And that we had those DAOs in the right locations to serve as gap-filling radars. We would not have seen those zigzag patterns without those DAO radars where they were. We also, I think, we're fortunate to have some new instrumentation and modeling capabilities like WRF Weather Mod being available to us, and the W-band cloud radar. But another very important component was our partners that we had in the field. So we worked with a very experienced team overall and had some great partners in Idaho Power that had excellent local forecasting expertise. We did not have a single bust case, right? Like this team forecasts for cloud seeding all the time, every winter for their operations. And so that partnership, that local expertise on the ground was critical as well. And as I mentioned earlier, I think we also had some good fortune because it was a very active winter. So where do we need to go? There are numerous challenges in this field. We've made some major advances, but there still are a fair number of uncertainties and remaining questions. We know that the conceptual model works to produce snow, but we need to better understand when and where does it work most effectively. And is that cost effective for what the end goal is? One of the things that we need to start doing more of then is moving into our ability to study what an operational program looks like. We did a research program. We forced us to look at airborne only. A lot of operational programs use ground-based seeding, for example. We need to better understand and quantify the impacts from ground-based seeding. And we need to also compare with some of the statistical analyses so that we can see and better understand how those two methods of evaluation compare, because that's the way that a lot of the operational programs work, is they use some statistical analysis. But we also need to continue to build confidence in our ability to quantify these impacts of weather modification and do so beyond just winter orographic precipitation enhancement. So all of these successes focused on winter clouds. Even though I showed how complicated they can be with the generating cells, they're still relatively simple from the fact that their updrafts are, single meters per second. They're not convective updrafts. But summertime convective precipitation enhancement is very widespread, especially around the world, even in central plains of the US. Sometimes it's for precip enhancement, sometimes it's for hail mitigation. We have a lot of unanswered questions, and even the advances we've made here, we still have to overcome some major hurdles to make advances in once we start moving into better understanding impacts of summer convection. And then education and public perceptions or misperceptions is another huge challenge here. It's really important that we educate folks on how cloud seeding works, what it does and what it does not do, and address common concerns, of which there are many. Every presentation I get on cloud seeding, I generally get asked the same questions. I'll be curious in this audience if I get some of those. We have to address those. I mean, it's very important that we address them, and in doing so, do what we can to overcome the mis and disinformation that's out there that gets linked to weather modification. So to do this, we need continued innovative research with improved methods and new technologies. There's a lot of new technologies that are happening right now that I think will really help us continue to make advances, such as the ability to use UAS for measurements, and AI and ML, of course, is on the brink of solving all of our problems, perhaps. Or not. But we also are going to need to go back into the field. We're going to need more field data, especially focused on ground-based seeding. It's a big challenge, but I think that's where we need to go next. With what we've been able to do with airborne, I think we can really put together some good ideas for how we can tackle this for ground-based seeding. And one thing that I didn't get to mention earlier, but Snowy did not collect aerosol data, but we found in many of our studies the sensitivity to that background aerosol, because that influences your cloud drop number concentrations, that influences your natural ice nucleating particles that are there. We really need to better understand the aerosol data, the aerosol conditions in these regions. We also need multi-state partnerships and or some federal agency support. You know, cloud seeding has largely not been supported by federal agencies. NSF funding Snowy was specifically because we didn't do the seeding. Idaho Power did. So we were doing the research for it. So it's been a great pleasure to work with different local partners over the years on this research, but you can imagine these issues don't stop at state borders or at watershed boundaries. And so some of the questions that we need to address, we need to do so more holistically with multi-state partnerships. And then we really do need to keep a stronger focus on education and engagement with the public. I will say, fortunately, we've just recently created the first COMET training module on cloud seeding. This is focused on wintertime orographic cloud seeding with some of the results from Snowy. We really need to continue to build some of these resources so that we have factual information available to anybody who is looking for it. So with that, I'm going to stop and take questions. I want to thank all of the many sponsors and states and everything that have worked on this, and all of my colleagues that have been working on these fun research projects and papers over the years, and let you sit in awe at what a Dow radar looks like when it's buried in snow on top of a mountain. When I made the argument to get the cover for BAMS, I said, I bet a lot of people see Dows for severe weather research, you know, tornado and hurricane chasing. You don't always get to see them in their less glorious state like this, so let's get that out there so people know that they're really useful for winter weather studies as well. So thank you.
Thanks, Sarah. That was great. I've seen some of your other shorter talks, so I'm excited to see what kind of questions you got too. Reminder for those of you online, you can ask questions through Slido, which is a little tab right at the top of your video screen.
Okay. In the spirit of potential misconceptions, you know, in public, somebody who's not a microphysicist, it seems to me that if you make the precipitation drop a little more efficiently upstream, you may reduce the precipitation downstream. Is that a concern?
Yes. I don't have prizes here, but Morris got one of the common questions that we always get asked. It's, are we robbing Peter to pay Paul? And you know, it's no surprise that I get this question, not just with the public, but in a scientific audience, because that question is rooted in our physics understanding of conservation of mass, right? But one of the things that we find and what we see in our model simulations is that doesn't really play out, not consistently. And part of that, I think, is because the atmosphere is not stationary. There's always fluxes happening. So if it was stationary, then that principle, I think, would come true a lot more often. But the other thing that we're seeing is that, and what a lot of these programs refer to is this overall water vapor budget. So we're talking about depleting water vapor ultimately from the atmosphere. The precipitation change might seem like a lot, But in the bigger picture of the overall water vapor budget, because we know that the water vapor is still there even if we don't deplete all of the water vapor, bottom line, okay? So there's still moisture elsewhere. And what we've seen in our model simulations sometimes is that you actually get downstream impacts that are increased as well. Because if you, like say you have multiple mountain ranges and they both are forming supercooled liquid clouds, mixed phase clouds with supercooled liquid water, they're both sitting, where they don't have enough natural ice nucleating particles. You simulate seeding and it impacts this mountain range, but if some of those particles make it to the downwind range, they might also enhance precipitation there as well. So it's not a clear-cut yes and no. It's, I think, potential. Like, I think some of the simulations where we see positives and negatives we think might be numerical noise. We're doing some investigation to look into that as well, because those of you that are modelers know that there's numerics that can build up over time and create noise. So we need to feel confident that these results are due to the physical change. But if there's a situation where we do see that that displacement of precipitation one way or the other, that's what we want to better understand. Because right now, operational cloud seeding programs in the US operate with suspension criteria, so they don't seed under hazardous conditions, avalanche warnings, flood, you get too much snowpack. That could become a suspension criteria. If we can better understand under what conditions that could happen. But that is not, to me, I don't think it happens as much as people are fearing that it does.
What do I do with this?
All right, question from online. Great talk. This is from Romulo Cruz. Great talk, thank you very much. I have two questions. Is there an impact in the biodiversity from AGI? Are there other alternatives to AGI? And then two, is there then a potential solution to the glacier retreats in different parts of the world that use the ice seeding with AGI?
Okay, so on the first question, the prize for this question. The other common question that I always get asked is about the environmental impacts of silver iodide. Good reason, right? One of the things that have been done in some of these projects is they've done trace chemistry measurements to try to detect the silver in the snow. Sometimes it's for the purpose of making sure that there's not adverse amounts of silver in the snow, water, or soil. But sometimes these have been, in the past, some of these studies were hoping to detect the enhancement of silver in the snow to be able to say, hey, that was seeded snow. So the downside to those studies is that was hard to do, to readily detect that enhancement in silver in the snow. So it wasn't being able to be used easily for an attribution study. But the good news is, it's such a small amount, it's very hard to detect in the snow. And of those measurements that have been done, the amounts of silver that were measured were generally on the order of the background amounts of silver. Silver is naturally occurring in the Earth's crust, and so we do have silver in snow from that. And during these seeding periods, it was really hard to detect enhanced levels. And the levels that have been measured, like in Wyoming and some of these remote regions, are multiple orders of magnitude below anything of EPA and WHO kind of concern. So right now, I don't see that as a major concern because it's such a small amount. If every mountain range in the western US were to start seeding all the time, and we're putting out that much more silver, we might be able to start to see some accumulations of it. Another thing, so I often say I think it's important that we set up some ongoing monitoring and things like that. But I think another thing that we're hoping to do with some of our current projects is use WRF weather mod to maybe even map out if there's any area where silver might be accumulating, and use that as a better way to guide where we take these samples also. Because it's also not clear if where the sampling has been done in the past was in the right locations. If we were expecting the impact to fall out in one place, but it was maybe falling out elsewhere. So I think there's room for some more investigation. At this point, I'm not terribly concerned. And cloud seeding is happening in our own backyard, and I'm still drinking the water because from the data that I've seen, it's a very small amount and hard to detect. Is there a potential solution to glacier retreats? Anywhere where we have, the overall goal of winter orographic cloud seeding is to increase the snowpack. So in places where glaciers accumulate, could this be a way to help enhance the snowpack enough? Maybe, I don't know. I think overall this effect is relatively small. We are owing to the natural weather patterns. We don't create clouds here, so we have to have weather patterns that create the clouds with supercooled liquid water to begin with. So if that's not present in the areas where we need that snowpack to accumulate, then we're already not going to be able to do much. So, and that's another thing we've been doing in some of our research is trying to better understand where the opportunities for seeding are. Every mountain range is not going to be equally the same in terms of how often there's supercooled liquid or how you might target that mountain range with seeding or for seeding. So I don't know. It's actually an interesting question, though. Like, where are the glaciers retreating and what are the cloud conditions there? Would they be considered seedable or not? And how much potential additional snowpack could accumulate from seeding? Could propose that project.
Hey, sir. So I forwarded you an article
Yes.
over the weekend. And so I still follow the Tucson paper. And the article was written by one of the science reporters that I still keep in contact with. And it is entitled, "Cloud Seeding to Boost Rain Snow Hasn't Proven Effectiveness," federal report says. And it references a study from the Congressional Government Accountability Office that did not find significant technological advances in cloud seeding. So maybe could you, for benefit of the audience, give a little bit of context on the GAO report, and the article does reference your work, and it's pretty long article. But what are your thoughts on the GAO report vis-a-vis what you presented to us here?
Yeah, so I think that report says they did find significant advances in the technologies, but there's still uncertainty remains. I think it's fair. I mean, I was on one of those panels. We do still have uncertainty. We have new capabilities, we have models, but there's uncertainty in those models. There is, I think it's a very fair article, and I think it's a fair report. 2003, the National Research Council came out with a report that also said, all these cloud seeding studies are inconclusive. At this point, that report says that they're not fully inconclusive because they do cite SNOWY and they cite the work that we've done that have fully proven the conceptual model. But with regard to its effectiveness and cost effective, I already rattled off a few of those questions. So I think it is a fair statement to say that there still is some uncertainty, and especially in the other types of cloud seeding, because they also did look into the summer convective, precipitation enhancement, hail mitigation. There's large uncertainties in those fields.
But you asked me what I thought of that, and I thought the headline belies all of those subtleties.
Yeah, the GAO report had its initial draft title also was like that, but they changed the title a little bit. But that's kind of, yeah. But I do think it's fair.
Okay, we have one question over here, and then we'll go back online.
First, this is an outstanding experiment. Years ago, I was on an academy committee. You've probably read that report. It said there was no scientific evidence for the effectiveness of weather modification except for orographic cloud seeding. And that was over 20 years ago, and you've certainly demonstrated that it doesn't work. I have a question related to cost effectiveness. How much does silver iodide cost, or how much did you spend on the silver iodide for this experiment compared to the value of 100 acre-feet of water?
So that's a great question. And let me be clear, we didn't spend that money on the silver because we're partnering with folks that are doing operational cloud seeding. But we have started trying to get into cost-benefit analyses, because the big challenge to the cost-benefit analysis is quantifying the impact. So there's still uncertainty in that impact. But what we're finding is that our best estimates using the modeling framework that we have now are on the order of tens to hundreds of dollars per acre foot. That is an order of magnitude more expensive than some of the operational programs cite in their reporting. So that's another reason why it's really important, I think, for us to try to compare more directly the modeling approach versus those statistical analyses that are being used to generate, because we have an order of magnitude difference, we need to understand where those differences are coming from so that we can, as a community, feel more comfortable with that outcome, with what those cost-benefit analyses are saying. By the way, the costs will vary from program to program. It's dependent not just on the cost of silver, but more on the number of ground-based generators, the types of ground-based generators, if you're using an aircraft, if you have a big team of forecast, like there's a lot of costs that go into it that's actually a lot more than just the silver iodide itself.
Okay, a question online from Jorgen Jensen. Very nice talk. When the model didn't predict SLD, which I think is supercooled large droplets, and SLD was observed, what do you think the model got wrong? For instance, was it because the bulk microphysics model does not track aerosol sizes within drops, and that giant aerosol properties were different between the different cases?
Yeah, so it's a little bit of, it's multiple reasons. There is a sensitivity to the background aerosol that we have seen, but in the case of the HER forecast, I think the background climatology aerosol that's used there was probably a minor factor. I think the bigger factor is getting the thermodynamic structure right. If a cloud, so for example in Snowy, we saw a lot of layered clouds with really shallow layers, dry layers in between them. If the vertical resolution of your model doesn't allow for that dual layer cloud structure, you're going to generate a deeper cloud with a much colder cloud top temperature that will appear glaciated in the forecast models. So that, I think, is one critical thing, is we need better vertical resolution in our models to be able to get those layers right and get the thermodynamic structures that create the clouds to begin with.
So my question was, so you gave a little information about the generating cells and what you think drives those. I was wondering, in the seeding lines, do those become reflective enough to be classified as generating cells? And if so, do they have the same sort of properties as the naturally occurring ones?
Great question. That's one of the reasons why I think it was so important for us to better understand what these generating cells were, because the seeding lines could look like generating cells because they are a focal point for ice formation with that trailing echo below it. But I think the dynamics are different, because the dynamics are driving that convective cell type structure in the generating cells, whereas we are just microphysically forcing ice to form in the seeding line. So I think if we, and actually I don't think we've looked into that with the seeding, I'd have to go back through and look at some of the data from our in situ seeding lines, but some of the dynamic differences that we see in generating cells, I suspect we wouldn't see unless there's a latent heat kind of microphysical dynamic feedback that takes place.
Right,
Which
yeah.
there might be some of, actually. I think we went in our new study with Chris.
Right, that is cool, because then you can sort of disentangle the cloud invigoration from latent heat release versus radiative cooling. So, thanks.
Yeah, we're working on that with our team.
Nice presentation. Last month we had a presentation at CAPEX. They looked at tropic tropics, how the cloud enhancement, the time started. The gap there was quantifying the QPE. Enhancement in DBZ about 35 or so, that kind of shows, but there is a lot of non-linearity between DBZ and rain. Same thing here, you showed about there is an increase in DBZ and second is point snowfall measurement. I think there's a big uncertainty in really quantifying how much really ice water equivalent or rain. That's, I thought there's a big uncertainty in all the studies. And that's like end product, if you look at it, all those work, what you're doing.
Yeah, so some of our team members, Troy Zaremba and Bob Robber, published a paper doing some back-of-the-envelope calculations for reflectivity enhancement, and would we be able to expect to detect that reflectivity enhancement in a seeded cloud? And basically, that study confirms that in a cloud that has background precipitation already occurring, the change from seeding is not going to be detectable. So again, another reason why here we've had success, because the background was weak or negligible. So we've been able to detect that pattern and the subsequent enhancement in reflectivity. But in those other cases where there's already ice forming, that change in reflectivity is not going to be detectable. And this is also why we have to rely on other mechanisms then for detecting the differences, which is why we're working with WRF weather mod. But again, WRF weather mod, we want to try to use as many observations as we can to constrain it. But yeah, spot on. That's a real limitation in those cases that have background precip. And it's not like we can only choose clouds that aren't precipitating to seed. Potentially, some of the bigger impacts could be in those cases that have stronger dynamics and already are starting to form precipitation. That's what we're trying to better understand, too, with the modeling.
Thanks, Sarah. Great questions. We've hit our hour, so we'll be respectful of everyone's time and wrap it up here. We all know Sarah's local to RAL, so you can go find her there. Her second to last slide was a great intro to next week's EOL seminar, which will be on Comet and what they can do for EOL or other groups at NCAR. So let's thank Sarah again for that really interesting seminar.